important.
Huh?
750.
Yeah, 7:45. Right at the beginning of the first block.
I want it.
Where's some max?
Way too long.
That's annoying. I don't even want to take it.
Don't ask me.
Is there any way that we could like get out of taking it?
Don't go.
Don't come.
Well, but they're still gonna take it. I mean,
Yeah.
so.
They'll crop you in, Matt.
Oh, I could sleep in. Let's go.
I mean, that's still
They'll
gonna take.
still be coming late.
Yeah, they're still taking attendance because that's
Were you
750.
angry this morning? I don't know, Chase Shervin is in my first block and he said you were angry.
Oh yeah, he said he came in, you were lecturing, and you were angry, or you seemed
Or,
angry.
yeah, you seemed angry
Until he
or
wasn't gonna
yelling or
ask you.
something. I said, that might just be him, but he also might be angry.
Let's go with that. Okay. Yeah, it's just Chase. Anyway, love him to death, but I can't read his handwriting. Okay.
So like Eli.
Huh?
So like Eli.
What?
Except he doesn't love Eli to get that today.
Okay.
He also didn't know my name, so.
He doesn't know Eli, he only knows McGrill.
Yeah,
No,
it's
seriously, it's like,
He goes,
That's why it took him a second.
it's like I saw your name, it's like, what the hell is that?
Whoa!
Oh, okay.
whoa, whoa, whoa.
All right, Mad Max.
Yeah, we're going. We're going.
Oh, all right.
Yeah.
Okay. Great. All right, any questions on the assignment? Great.
Okay, so is there a few ways you can find the last problem, number 6?
Yeah.
Okay, and would one of those ways just be like what I did? So I just plugged in a value for R, and I would divide that by 37, by the velocity, and I had to make sure that it was less than or equal to 6 seconds. And
No.
closer to 6, the better.
No,
I don't think you.
that won't do it.
Okay, well, I'm sure.
Because there's so much, no,
Unless you're super.
no, that ain't gonna happen.
Okay. I don't know how to do
Okay,
that.
so, look, let's back up to number 5. Okay, let's back up to number 3, actually.
All right.
Let's do the whole thing
No.
together.
Okay, because if your answer to the time on number 3 is wrong, everything else is going to be wrong. So your total time on number 3 should be 6 seconds,
Yep.
okay? Because if that's wrong, everything is going to be wrong, okay? And your max height should be around 44 meters, okay? That's going to be an important part of this story. So when you get to number 5, you should see that he clears the wall and the height should be around 4.5 meters at that point, okay? So when you're 220 meters away and you shoot this ball, and here's this wall, okay? And this is 220 meters. So the only way you can do this is to go, oh, range equals Vx time. You know how far it's traveled. You know your initial velocity. You find your time. Plug that into 1/2 AT.
Oh, it's a bomb.
1/2. 1/2 AT squared, okay? Once you get this time, plug it into here, see if it's above 2.2 meters. And it should be like 4.5. So basically, and this is where you want to think about an answer before you even start the problem. So on number 6, I'm asking, how far back can you be where this thing just clears the wall? Okay? Just clears the wall. Well, you know your answer to number 6 has to be more than 220 meters. Because at 220 meters, if you shoot it there, you're about 4.5 meters above the wall. So if you move this whole thing back, then you're going to move that curve back until at that point you're at exactly 2.2 meters. Okay? There you have it. So you know at 3 seconds into the flight, you're at your maximum height, right?
Right.
You know that.
Yeah.
And at that maximum height, you're around 44 meters. So here's the deal. When this thing starts to fall, okay, it's like a lemming problem. When it starts to fall, what's your initial vertical velocity? 0. Okay, my initial vertical velocity is 0. Now, if it fell all the way down to 44 meters, how long would that take?
3 seconds.
3 seconds. right? But is it gonna fall all the way down to the ground? No, it's gonna only fall from 44 down to 2.2, right? So if you take 44 and subtract 2.2, that's the distance that it has to fall. Then you can take that and plug that in for here and go, oh, that's the distance that it has to fall. Yes?
Is that 2.4 because of height?
Yeah, 2.4, what did I say?
Okay, you said
I was thinking
2.2.
220, confused, yeah, it's 2.4, my bad, 2.4. But on the way down, what's your initial velocity? 0. Okay? So this whole thing drops out. So you're going to take 3 seconds. Now, on the way down, because it's only fallen to 2.4 meters, is your time going to be bigger or smaller than 3 seconds? Smaller, because it's not falling all the way down, right? So basically, you're going to take 3 seconds, add that to how long it takes to fall from 44 down to 2.4, add those two times together, multiply it by Vx, boom, you're off to the races. Okay? A little bit bigger than 220. It has to be bigger than 220. Yeah. Now, here's the other way that you can do it. If you're into math, you know you want this distance to be 2.40 meters, and then you've got 1/2 negative 9.8 meters per second squared times t squared plus, now what's the initial vertical velocity? Way back on problem number 3. What's the initial-
29.4.
Huh?
29.4.
29.4 meters per second times time. So what you can do is solve this as a quadratic, okay? And because you know this, get like linearly, solve it as a quadratic. You know, you have negative b plus or minus b squared, all all that good jazz. And get everything on one side, solve for 0, and basically you're going to get 2 possible routes for time. One where it's over here on the way up, and one on the other side when it's on its way down. That's the other way that you can do it. This is solved as a quadratic.
So wait, which one of those would you choose?
Would be what?
Which one of those would you choose?
If it were me, I'd solve it as a quadratic.
Oh, okay.
But
I mean, like the 2x values. I mean, fine.
you'd have to find the bigger one because that's going to put it on the way down.
Oh, okay. Yeah.
Yeah. Okay. Anything else? Going once, going twice, so. Okay, get that, here we go.
We need to bring them
All
back
right.
together.
Spray paint based off
No, because I would take offense to that because.
Okay, no. What if like we made like a paper mache eagle head and like taped it to the top of the bowl and then like we put wings on the bowl?
That'd be good. That's a lot of effort, and
Think
I
of
really
the
don't
old
think that
process, then?
you would put in that effort.
Okay.
I feel like you.
All right, so here's the next big thing, which is going to be circular motion. So don't forget, Monday you can have a simple quiz over projectile motion, but we're done with projectile motion. Now, so moving on to circular motion, which is something we haven't talked about yet. So here's the deal. I'm going to take this thing, I'm going to get this rubber stopper swinging up over my head, right? So once I get it up to a constant speed, is it accelerating at this point?
No.
No. Why not?
Constant velocity.
Constant velocity. Okay, you all keep that in mind, and let's go to the back.
I hope so. That would be really nice.
Think about how much shit this was.
Now, see, I had an epiphany about this last time we were talking about projectile motion. The acceleration is inward along the spine.
Yeah, if you have to.
Go back to English.
I
I'm a genius.
I know.
Memory loss will be due.
How do you want this set up here? Is that pointing towards the thing?
Okay. So what we have here is called a liquid accelerometer. And all this is just water with food coloring in it. And everybody asks, is that like blood of a freshman? No. Thought about it, don't get me wrong, but no.
Can we put
So-
blood in it?
Huh?
Can we put blood in it?
No.
Why?
It's biology.
It's fun.
If we just if we
No, no,
Every couple of weeks.
Just every year, someone
No.
new donates their blood. It works.
no.
The other day.
Okay.
Cool.
So here's what I've got. I've got a 50-gram mass suspended from the end of the string. And I'm going to let go of this, and we're going to see what's going to happen. So there's three possibilities that could happen to the liquid that's inside of here. When I let go of it, one option is that it's at rest and it's going to remain at rest and it's just going to stay completely level. Okay, that's an option. Option number two is going to get pushed to the back and it's going to move back like this. Or it's going to go in the direction of the acceleration and because it's accelerating that way and it's going to start to slant up this way. So it's either going to stay level, going to slant up towards the back, or it's going to slant up towards the front.
I'm gonna go back. I'm gonna go with the,
Just like
I'm gonna go with the back. Yeah, imagine.
Step on it, boom, boom.
Okay.
I like Maddie.
Exactly. It's like we got the
Maddie's explanation was good.
Oh,
What's Maddie?
I said, I think it's gonna go back and then it's gonna go back to the middle.
Love.
And be level.
So it's going to initially going to go back,
Yeah,
Yeah.
and then it's gonna go.
then it
There's
will
constant
level off.
acceleration.
Yeah.
but
I know how to explain
Acceleration is
this. Like,
constant.
know when you're taking a drink in the car and someone slams on the brakes and it goes forward, then it comes all over you too.
Yeah.
Perfect
Okay,
example.
but the acceleration is constant, so it's not going to go back forward, because it doesn't stop accelerating until you stop it, which I assume not cool.
Okay. So let's lay this out. Is everybody cool with the idea that it's going to go slant towards the back?
Yeah.
Okay, now let's just deal with that at the beginning first. So here's the question. And let's go back to something that Grape said, okay? Like if you're in your car and you press down at the gas pedal and you're like pushed backward. So here's the question, and this is important. If it actually does go to the back, is there something in the front of the cart pushing the liquid in that direction?
No.
No.
It's just its inertia.
It wants to stay at rest.
It wants to stay at rest, right? Okay? So if you're in your car, you press down on the gas pedal, is there something inside your car pushing you back into your seat? No, there's not. Okay, but what does your body want to do? So you feel the action-reaction force of that chair making you accelerate forward. But there's nothing inside of you or inside of the car emanating a force that you can't see pushing you into the back of the chair, right? So you're saying that there's nothing in front of this thing pushing it to the back. So what does the liquid want to do? Say rest. Why? That's inertia. Mother Nature's lazy, it doesn't want to move, right? Now, what if I could do this? What if at the very instant that I let go of this, I could make the back section of the accelerometer disappear? Okay, so in other words, this back section would go at the very instant I let go of it. What would the liquid do?
Go down. Could it stay and fall?
So it would just stay in place, right? This would accelerate from underneath it, the water then would just fall straight down, which would be cool, right? Okay, so we're gonna let go of it, we'll see what's gonna happen. Okay?
Oh. See that?
Okay. So when I let go of it, right, we get a little bit of a slant towards the back. Now, we're gonna change it up a little bit. So swap that out with that one. So now we're going to go from a 50-gram mass to a 200-gram mass. So what do you think is going to happen to the liquid? Acceleration is going to be bigger, right? Why?
It's deeper.
More mass.
Yes.
More force, right? Okay, more force. So what should happen to the slant? Bigger?
Steeper.
More dramatic. Okay. Let's see what happens. When I let go of it,
Oh.
okay, hook that back up. Okay, we'll do that again. Right? Okay. So, let's look at what happened. What was the direction of the movement of the liquid relative to the direction of the acceleration? Opposite, okay? So the liquid moves in the opposite direction of the acceleration, right? Everybody cool with that? Now, if it's moving at a constant velocity, what's going to happen to the liquid? It's just going to stay level because, so the liquid only tilts when something accelerates, okay? Let's remember that. The liquid only tilts when it accelerates. If it's at a constant velocity, it stays level. Y'all keep that in mind. Okay, let's go back. Hold that out.
Who didn't check it?
Okay, so here's what we're gonna do. I'm gonna have Bree hold this thing out, eventually like all the way out like this. And then I'm going to spin her at a constant speed. Okay? Now, if this thing isn't accelerating, what's the level gonna do? It's gonna stay exactly level,
What's the level gonna do? It's gonna level.
Gonna level.
right? Now, Shively, what do you say?
I think the liquid's gonna move out because, like, you know when you get a bucket of water and you like,
Ooh.
it stays in it.
Okay?
So,
Ooh.
There's
That's
inward
gotta feel-
acceleration.
Hold on to
that's
that
going
thought. Hold on to that thought.
Yeah.
Okay, you're on step 4. Okay?
We need to be on one.
Yep. Now, here's the, though, because you all said, when I was swinging the rubber stopper around, you all said that it wasn't accelerating, right? Okay? So by that same thought, if I spin this thing around and it's not accelerating, what's it going to do? It's going to stay exactly level,
Yes.
right? Okay? Now, does anybody want to change their vote? Mad Max?
There's inward acceleration.
So it's going to accelerate.
Yeah. There's,
Why?
Well, I don't know exactly why, but I know it does accelerate.
What do you, depends, say this, which, centrifugal force.
It's like whenever you like go around like a ramp.
Hold that thought, hold that thought. Now you're on to step 6.
Okay.
Matt?
Is it accelerating because it's changing direction?
Oh!
Good job, Matthew.
Whoa.
That's a day one.
Okay, are you ready? So we're gonna spin this thing around,
Oh, it's honestly.
Okay.
Oh, wow.
okay? Now, as she slows down, what happens?
slope decreases.
So as she spins slower, what happens to the amount of acceleration?
It lessens.
It becomes
Less.
less. So if we spin pretty fast, you ready?
Yeah.
Okay? Okay? But then when we stop, goes back to being level. So this is important. Which direction did the water move?
Out.
To the outside. So what's the direction of the acceleration?
In.
Inward. Okay? So the listen to me, this is important. This is one of the most important things you have to understand. The acceleration is inward. Okay? All right. Well done. Thank you, Joe. Nicely done. So, you can run for a read? Nice.
So, would you say that the acceleration is opposite from the movement of
The liquid.
what?
Of the liquid. So
Okay.
the liquid meant to move to the outside. So, now, let's look at this rubber stopper, right? And I'm going to swing it around, and this is like looking down from on top. So when I take this rubber stopper and I swing it around like this, okay? What does the rubber stopper at any given instant want to do?
Move towards.
No.
Just
It wants to move in a
Straight.
straight line at a
Constant
constant
velocity.
speed. Because remember, because here's the problem. Up to this point, we've been talking about vector quantities. And any vector quantity has two things. What does it have?
Direction and
Direction and
magnitude.
magnitude. So everything that we've talked about so far in terms of acceleration has been changing what? The magnitude or the direction?
Magnitude.
Magnitude, right? We've been talking about changing the magnitude of the velocity vector. So if you look at what happened with the cart, okay? So here was the cart, okay? And then we had a string attached, boom, okay, like this. So when we let go of it, that tilted towards the back, right? So our acceleration vectors started off at V1, and then it became bigger at V2, and then it became bigger at V3. True? So here's the question. What's the direction of my acceleration vectors? To the right or to the left?
To the right.
To the right. Why?
The liquid's going that way.
Because what?
The liquid's going
No,
that
no,
way.
no, 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 no.
It has a
Because
positive
the force of
velocity
gravity.
No,
acceleration.
no, 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 no.
The velocity is
You're
pointing-
complicated.
Velocity is to the
The
right.
force is
Which
going in that
direction are my
direction.
velocity vectors changing?
This way.
To the right. Okay? The velocity vectors are getting bigger to the right because gravity is pulling down on this. Okay? So here's what's important. My acceleration vector points in the direction that my velocity vectors are changing. Okay? Go with this. Because Mother Nature never wants to change the velocity vector. So up to this point, we've only been talking about changing the magnitude of the velocity vectors. So what's the purpose of the gas pedal in your car in terms of a velocity vector? Make the velocity vectors bigger. Okay? What's the purpose of the brake?
To make them smaller.
Make them smaller. Now, what's the purpose of the steering wheel?
To change their direction.
To accelerate by changing the direction of the velocity vectors. So if you change either the magnitude or the direction of the velocity vector, what are you doing?
Accelerating.
Which requires a
Force.
force. Because without a force, Mother Nature isn't going to change the velocity vectors. Okay? Got that? All right. So, when I swing this thing around, and when I let go of it, what's it going to do?
Go
It's
flying.
going to fly in a straight line, right? When I let go of it, why is it going to, which would be cool, but as soon as I let go of it, what's it going to do?
It's going to fly off.
Fly off on a straight line. McGregor, you throw in a discus, I take it?
Yeah.
Okay? As soon as you let go of it, what does it do?
Good, straight.
Does it ever like curve like that?
Yeah.
It's because
Well, like,
he's bad at throwing it. That's
no, it's
why.
because like, depending on the angle you throw it, the wind will pick up on it.
Okay, no. Let's leave wind out of it. Okay?
So non-realistic.
Yes.
It goes straight.
It goes straight. Okay? Thank you. Okay. So here's the deal. This is looking down on top of me as I swing this thing around. So if I let go of it at this point, what's it going to do? It's going to go in a straight line like this. If I'm here and I let go of it, it's going to go in a straight line like this. If I'm here, it's going to go like this. So is the velocity vector changing as it goes in a circle?
Yeah.
Yeah.
What are we changing?
Direction.
Which direction is the vector changing? Towards the inside? Is it being pulled towards the inside or towards the outside?
Towards the inside. Towards the inside.
Towards the inside, right? Because this thing is continuously being pulled towards the inside, right? Okay, it's continuously being pulled towards the inside. So, if this is the direction that is changing, what's the direction of the acceleration?
Outside. Inside. It points the same direction.
Yes, your acceleration always goes in the same direction that your velocity vectors are changing. Just like we did down here, right? It's the exact same idea. So, guess what? My acceleration vector points towards the inside, which is why when Bree had that accelerometer and she swung it around, okay, what did it do? Where did the liquid go? Towards the outside, in the opposite direction of the acceleration. Got that? Okay. So, my acceleration vectors are always pointing inward. Now, if my acceleration vectors are always pointing inward, which direction do you think the force is acting that's causing the acceleration?
Outward.
Love of?
Oh wait, sorry, never mind.
Inward.
Okay, great,
Okay,
great,
I got excited.
great, great. if I want to make the golf ball accelerate that direction,
I understand.
which direction am I going to hit it?
I'm gonna hit it in that direction.
I'm going to hit it in that direction. So if I want this thing to accelerate inward, guess what?
Gotta put that force inward.
Oh, I got to put the force inward. That's kind of cool, right? Now, notice that I put this subscript C beside it. The subscript C stands for centripetal acceleration and centripetal force. So, now, let me explain the origins of this word. So this is centripetal, okay? Centripetal comes from the Greek word meaning inward seeking, okay? So, your centripetal force and your centripetal acceleration, listen to me, there is no exceptions to this rule whatsoever. None, zero, zip. Your centripetal acceleration and your centripetal force always act at right angles to the instantaneous velocity vector, and they always point inward. They never, ever, ever point outward, okay? They always point inwards and at right angles to your velocity vector. Okay, so there's two parts to that definition. When I ask you, hey, what's the direction of your centripetal acceleration? There's two parts to your answer. It's always inwards, and it's at right angles to your instantaneous velocity vector. Okay, no exceptions whatsoever. It's never outward, it's never on a tangent, nothing. It is always towards the center. Got that? Okay, now, stop that, I gotta hand out some notes. We just established that everything is acting inward, right? Here's the problem. It's counterintuitive to what you normally experience when you're moving in a circle. And let me explain. So let's say that here is an intersection, right? And you're driving along, and you're going to take a hard right-hand turn, okay? So let's say that McGriddle is driving his Jeep, okay? And so this is looking down on top, right? So here's the Jeep, and here's the steering wheel, right? And here's McGriddle, little facial hair, and he's got both hands on the wheel, right? 10-2, not distracted, not looking at his cell phone, not texting, nothing, okay? Solely focused on the road ahead, checking his mirrors occasionally, right? Okay.
I don't stick shift, so I'm gonna go
Okay, all right, every once in a while. Okay. So here's the deal. So McGriddle drives along and he takes a hard right-hand turn. Okay? So he's going to take a hard right-hand turn. Now,
baby.
what are you going to feel?
I want this way.
Okay?
I'll
Now,
go the way I'm turning.
oh, right.
Body roll.
Okay? So he's going to feel like he's being pushed against the outside of the door. Because he's going to take this hard right-hand turn, he's going to be like, whoa! Okay? Right? That's what he's going to feel. And if I asked him, I said, hey, McGriddle, you took the right-hand turn. How did that feel? Oh, Mr. Burkhammer, I was pushed against the door. Now, let's think this through. And that's what you experience. And this is what Bree had mentioned, okay, which is centrifugal. Okay? Centrifugal comes from the Greek word meaning outward seeking. Okay? So that's the difference, because centrifugal means outward seeking. So let's think this through, okay, and see if it passes a logic test. So if McGriddle was right, he's saying, oh man, something pushed me towards the outside. So what that would mean is that something inside of his Jeep, okay, was emanating a force that you can't see, okay, it's invisible. Okay, it's invisible. It interacts with you, okay, and it forces you to the outside of your car, okay? You can't see it. It's invisible, but it pushes you against the car door, okay? Then, as soon as you make the turn and you straighten out, what happens? The force stops, okay? So, inside your car, there's this magic source of a force that emanates and pushes you against the car door, and it ties in with how tightly you turn and how fast you're traveling. Because if you're traveling really fast in a really tight turn, you go, whoa, okay, right? Or if you've ever ridden any carnival ride, right, where you go around in a circle, okay,
Yeah.
right? Tilt-a-whirl, whatever, right? Okay, that's the thrill, and everybody goes, oh, I'm being pushed against the outside. But is that actually what's happening? What does McGriddle want to do? McGriddle wants to go in a straight line. So imagine this, we won't do this because we like McGriddle.
Oh, come on. Oh,
I said we won't do it.
let's do it.
Okay, so we're going to take this car and we're going to put in frictionless seats. Okay? We're going to take out a seatbelt and we're going to remove the door.
See ya.
What nerd has
Okay.
built a Jeep?
Frictionless seats, no seatbelt,
Good.
door's gone. Now he tries to make the turn. What's going to happen?
He's gonna keep going straight.
Well, hold
Okay.
on. He's not going to
He's
go
gonna
anywhere.
keep
He has
going.
frictionless seats. He has no acceleration.
Then the back is there. He can make him
Oh.
speed up.
Okay.
Yeah. He just doesn't work side to side.
He's gonna
Okay.
keep going straight.
He's going to keep going in a straight line. Now, is there anything pushing him to the outside?
No.
There's no force pushing him to the outside. What does he want to do? He just wants to go in that straight line because of inertia. Okay? Now, if you're in a drone up above and have an understanding of Newton's laws, well, let's say that we're back to a normal Jeep. If you're in a drone up above looking down outside that frame of reference, you're going to say, oh, right, he's going to be turning. He wants to continue in a straight line. Therefore, there must be some force acting towards the inside to allow him to make that turn. So this is what's known as a frame of reference experience. If you're McGriddle inside that Jeep, you're going to say, oh, I was pushed against the outside, because that's kind of what he feels. But if you're on the outside looking in, you go, no, there's nothing inside of here pushing you. You just wanted to go in a straight line. The car door prevented you from doing so, and that's why you felt that. So it's the same idea of what Great brought up earlier about your car. So if Bree is sitting here like this, and I come up behind her and push her, okay, she's going to go like this. Okay, she's going to feel like she was pushed back into the car, into the seat. But is there anything in front of her pushing her back? No. Bree, what do you want to do? You just want to stay at rest. So she feels the action-reaction force created by the back of the chair. There's nothing in front pushing her. Same thing is true of McGriddle. There's nothing inside the car pushing him against the outside. He just wants to move in a straight line. He feels the action-reaction of the door. Got that? Okay. Now, here's the anomaly about centripetal force. Is that when you look at the four fundamental forces, gravity, electrostatic, weak nuclear, strong nuclear, you'll notice that the centripetal force is not listed there. Okay? It's not one of the four fundamental forces. So here's the anomaly about this. Centripetal force, we spend a lot of time talking about it, but it doesn't exist in and of itself. It only exists because of something else that's present. Okay? So I get centripetal force because of the electrostatic force that's holding the string together and allows me to swing this thing around. Okay? So one source of centripetal force is like a tension in a string. So when you look at sources of centripetal forces, one is going to be tension, okay? Or some mechanical device that's going to allow this thing to turn, okay? You can have something there. Tension could be a wall, something like that. Now, what's another source of a centripetal force? Gravity. Okay, we'll get to friction in a second. Gravity, right? So gravity's kind of a cool thing. We wouldn't be here without it. So here's the, not to scale, here's the sun, here's the earth, right? We're going around like this. So is the earth accelerating as it goes around the sun?
Yeah.
Yes, that's a good thing. Okay? That's a good thing. Because if we're not accelerating towards the sun, what are we doing? We're going off on a straight line tangent, much like that rubber stopper, which means we're going to get awfully cold, awfully dark, really, really fast. So the last thing I want to see is the headline from CNN. NASA announces loss of gravity in the universe. We are screwed. Okay? It's called our reality. We are screwed. Now, does the moon orbit the Earth?
Yeah.
Yeah? Guess what? It accelerates towards us because there is gravity. Okay. So gravity is kind of a cool thing. Now, there's a third one. Somebody said it. Friction. Ah, that's kind of cool, right? Because look, let's say you walk out this door and you need to take a right. But let's say that I put down the magic frictionless surface just outside my door. As soon as you walk out that door, are you going to be able to turn? No. No, what's going to happen?
You just go
You're just going to keep going in a straight line, straight into the locker. It's like, yeah, okay. So when McGriddle wants to make this turn, what are you going to do? You're going to make this turn. What are you going to do?
Hold on, turn the wheel.
You're going to turn the wheel, right? Turning the wheel is going to do what?
Change the direction of the car.
Change the direction of the car, right? Because of
Friction.
friction. Now, let's say that we've had a massive ice storm and this intersection is just a sheet of ice, okay? McGriddle comes along, he tries to turn, and he turns the steering wheel. What's going to happen?
He's gonna slide.
You're going to keep going in a straight line because there's no force to cause this centrifugal acceleration, right? He's going to, because of inertia, he's going to go in a straight line. But let's say that McGriddle being McGriddle, let's say that there's a big telephone pole right here. And he happens to have like the Indiana Jones like whip thing, right? So how can he use the whip or a grappling hook or something like that to make the turn?
Whip on the telephone pole.
Oh, Felix, what'd you say?
Gonna whip onto the pole and do a little 180 right there.
Okay, how about just a 90? You can do a 180, you know. Let's just do a 90, okay? So, but he had a 360, he goes all the way around. So, he's going to anchor this, wrap it around here, and then he's going to come around. Now, at that point, he wants to go ahead and go straight. So then what is he going to do? Let go. Let go, and then he's going to go about his merry way, right? So you could use a string to make that happen. Now, I don't recommend this, but we could also build like a concrete barrier. Okay? Build a concrete barrier, and the cars hit that, and they go around that way. Brutal on your paint job. Okay? It's probably not a good idea. So that's an option, right? Now here's the third option. This would be the coolest one. Let's say that McGriddle had as a superpower the ability to have very, very massive small objects appear out of nowhere. Okay? So if he could have a very, very massive object appear right there on the corner, he could basically pull himself into orbit, okay? Orbit this point, and then snap his fingers, that goes away, boom, he continues on his merry way.
That's very cool.
It would be very cool.
You're giving me some movie
Wait a second.
ideas.
What is that?
Oh, it's a car rolling out.
Wow.
Wait,
I literally heard it in my
It's
ears.
the CIA helicopter.
Okay, yeah, that's what it sounded like.
I know, believe me, I hear
It's
them
a
all the
thought
time.
police.
Okay, so typically, what do
Not
you
like
need?
George Orwell in that classroom.
Friction.
Friction, right? That's a cool thing. You could use tension, it's a little bit dodgier. Gravity, okay, that's the big mover in terms of the whole universe, right? So those are going to be your big three. Cool with that. Okay, stop that, stand up, take a
Can you draw me? Draw me next. Just draw a spaghetti noodle.
That's good enough.
What's your man, Max?
Impeccable. The likeness is uncanny.
That's great.
I'll give you $20 for it.
I can save it and print it out.
I mean, don't I get a percent of that because I'm the person depicted, right?
Yeah.
What's my cut, like 25%?
Oh yeah, easily.
All right, cool.
I'll give you a 5 spot.
Oh, it's Matt. Oh, they just started paying attention.
Yeah,
so.
they're kind of
Yeah, we
lame.
didn't know. Yeah.
We're just getting payback.
Hunter's big nose.
There's no Matt's in it. One day we should have Matt come in and play his guitar. He's in a
Yes.
band.
I am in a
You gotta do
band.
that. You gotta play a
Wait,
guitar.
Burkamp, I'd really like to finish that video you were showing us about the world.
I got boring after that because it'll start talking about history.
Okay, you were passing out.
You were.
I've had back problems, so I haven't been sleeping that well at night. So, you know.
Burkamp, I'm always down for a good old hat.
I know, so am I. However, okay. This is my lecture, that way I don't fall asleep. Okay, so here's the deal. So let's say that we've got a car going around in a circle, right? This is going to be important. It's going to be going around in a flat circle, okay? So, what are the forces acting on the car is traveling on a circle, in a circle on a flat track?
Gravity.
Gravity. Which direction is that going to act?
Down.
Okay, so we've got some gravitational force acting straight down. Tori, what's another force?
Friction.
Which direction is that going to act?
Opposite.
Of what?
Friction.
I got that, but which I got the friction thing, sweetheart. Okay? But which direction is it going to act? I'll give you a 50-50 shot. Okay? The friction is either going to act inward or the friction is going to act outward. It's a 50-50 shot.
What's it right?
I'll give you a hint. The last four letters are W-A-R-D.
That is a straight number.
Is it a 6 or 7? Outward.
It's either inward or outward. Sure. Be sure.
Okay.
Inward.
Yeah.
Yeah, there you go. Okay. So, now we'll get into why that acts inward in just a second. Okay. So friction is going to be acting inward. Now there's one more. Hunter. I realize that. That's why I called on you. That wasn't the question. Okay? I know you're here. That's why I called on you.
Are you okay?
You sound like you're yourself being attacked by a lion, man. Hunter, yes, I know you're here.
Yeah.
What's the third force?
Force applied. Yeah, friction.
Say gravity. Hey, say gravity. Just say gravity.
Gravity's already up there too.
It rhymes with normal. Normal? There you go.
Don't clap. Don't clap.
Because gravity's pulling the car down, right? The surface is doing what? Balancing that out, and friction is acting inward.
Oh man.
Okay. Now, why do I know that there has to be an inward force acting on the car?
Otherwise it wouldn't turn.
Because it's going in a circle.
Because it's going in a circle. Oh, that's kind of cool, right? And we said that any force that makes something move in a circle acts which direction?
Inward.
At
90
to the
instantaneous velocity vector.
instantaneous velocity vector. Okay?
Got it.
All right. So, let's look at definition of mu. Basic idea. How do you calculate mu?
FF over FN.
Force friction over
Let's go.
force normal.
That's cold.
Now, what's the frictional force creating?
Centripetal force?
It's creating the centripetal force, right? Okay? The frictional force is creating the centripetal force. Because if there wasn't a frictional force, what would the car be doing?
Sitting there.
It would be going in a straight line. So the centripetal force is created by the frictional force. Now, because we're on a flat surface, force normal is the same as what? Your gravitational force, right? Which is going to be Fg. Now, if you do a little bit of substitution, centripetal force, and we'll get into this in just a second, is mass times your centripetal acceleration. Okay, that seems reasonable. And then your gravitational force is mg. Okay? So one way to look at mu and something moving in a circle is that it's a ratio of your centripetal acceleration to your gravitational acceleration. Now, does anybody remember the theoretical limit of mu?
1.
1. So if your car tires have a maximum coefficient of friction of 1, what is your maximum centripetal acceleration then? If this equals 1, okay, what's your maximum centripetal acceleration that your car can pull?
9.8.
Or just 9.8 meters per second squared. Right, so that's your maximum acceleration that your car can undergo if you have good tires with a maximum value of 1. Okay, now, here's where the math turns into this. So, the simplest way to calculate centripetal acceleration is v squared over r. This is what's on your equation sheet, okay? This is a calculus thing because it's the rate of change in your velocity vector. So, but let's just look at it from the units. So the velocity is going to be measured in what? Meters per second. But that's going to get squared. And then the radius is going to be in meters. So we're going to have meters squared over second squared divided by meters, and I get
Meters per second squared.
meters per second squared. Which is what acceleration should be measured. Okay? So that's why it has to be v squared over r, otherwise the units don't work out. Okay. So, then oddly enough, centripetal force equals mass times centripetal acceleration, which we can also write as mv squared over r. So, here's where this thing plays out. Since it's v squared over r, if the radius stays constant and I double my velocity, what's going to happen to my centripetal acceleration?
Quadruple.
What'd you say, Honus?
Quadruple.
Why?
Just because that's what I remember happening when you square a number, you double it.
Well, look, what's 2 squared?
4.
4. If you double the velocity, you square it, it becomes 4v squared. So if you double your velocity, you're going to quadruple the centripetal acceleration, and then you're also going to see a 4-time increase in the force. So remember that if you're driving, and it's a Friday night, you're driving through a neighborhood, and there's a curve, okay, and you take it, say, at 10 miles per hour, okay, and your buddy says, wow, 10 was cool, let's try it at 20. Okay, so if you double your speed, guess what? Everything's going to get multiplied by a factor of 4. Okay, you're not doubling it, you're going up by a factor of 4. So keep that in mind. Now, let's get back to this in just a second. So, I'm going to take this rubber stopper. God knows what answers I'm going to get from this one, but let's ask anyway. So, I'm here. I know you're here. Okay. Great. Since you're here, okay, I'll call on you because I know you're here. So, great. I'm going to have this thing moving at a constant speed. Okay, now listen to what I said. It's a constant speed. So, let's say, for example, we're going to have Olivia, we're going to take her, and we're going to go out in her car, and we're gonna have her drive around in a circle in the parking lot.
Ooh, donuts.
You mean
No, just, we're gonna have her drive around in a circle.
A light
Okay.
circle.
So, what, Olivia, what's the easiest way to figure out how fast you're moving?
My speedometer.
Yes, we're gonna look at her speedometer and it's gonna read 10 miles per hour, okay, whatever that is. So, she's gonna be traveling with a constant speed. Okay, so I'm gonna say, hey, Olivia, I want you to drive a certain radius at a constant speed, right? Okay, that's gonna be important. She's gonna constant speed. But is she still accelerating?
Yes.
So her speedometer isn't changing because we're not changing the
Magnitude.
magnitude. But she's accelerating because we're changing the
Direction.
the direction. Okay? Cool with that. So one way to get the speed is if you're in a vehicle that happens to have a speedometer, you look down and go, oh, we're going 10 miles per hour, whatever that is. Now, but if I take this, right, and swing it around, I don't have a speedometer. But great, what's one thing that I could measure as this thing goes around?
The degrees, or, I mean, you measure the angle at which,
You're making this what we do.
okay, yeah, I guess you could measure the time it takes
Oh! I can measure the time for...
one revolution.
Okay, so as this thing goes around, right, we can measure the time for one complete revolution. So what do we use if you're talking about something coming back and repeating itself in an orbit?
The
RPM.
period.
Represented by?
Capital T.
Beautiful, okay? So we can measure the period, which would be the time for one complete revolution, okay? You can take a stopwatch, this is what you're gonna do in the lab tomorrow. You can take a stopwatch, you can measure how long it takes to go around, okay? So we got uppercase T. And we use uppercase T because it's gonna come back to that same point in its path, okay? What else could we measure?
The radius.
The radius. Ah, right, we can measure the radius, right? So, knowing the radius, Mary, what else could I find?
The diameter?
I could, but I don't care.
Well, you could find the circumference.
Ah, I can find the circumference, right? Oh, I can find the circumference. Now, Mary, as a follow-up question, in case you didn't answer present, how do you calculate the circumference of a circle?
Is it like 2 pi r?
It is.
Yeah.
Now, basically, all I'm doing is I'm taking the distance that the rubber stopper travels, and I'm dividing it by how long it takes. So if I take a distance and divide it by time, what do I get?
The velocity.
I get a velocity. Oh, that's how fast the rubber stopper is moving. Y'all have worked with this equation before. On the very first test, right, you had Mars moving around and spinning on its axis. And you figured out how fast Mars was moving in kilometers per hour and meters per second. Y'all have worked with this equation before. It's nothing new, okay? We're just applying it in terms of a rubber stopper moving around in a circle. That's all. Now, we're going to do a little bit of hocus pocus. Just a little bit.
A little bit of bonus.
So we said centrifugal acceleration was v squared over r. True?
Yeah.
So if this equals 2 pi r over t equals velocity, could we take this, perchance, and put that in for the velocity?
Sure.
Of course. I think it's easier. So I'm going to have 2 pi r over t. That's all going to get squared, and then I'm going to divide by r. So, what do I get when I square everything up on top? Garrett, what do I get when I square everything up on top? I square everything up on top. I square 2 pi r over t. What do I get?
You have 4
Yep.
squared. R
Yep.
squared, or t squared.
R squared over,
T squared.
right? And that's all still going to be divided by r. So this is like the pirate equation. 4 pi r squared over t squared divided by r. But now, this is where the pirate doesn't like this equation. Because what can I do with one of my r's? Oh, we're gonna lose one of the yards. So I get 4 pi squared r over t squared. Oh, that's kind of cool, right? So do I get units of meters per second squared? Yeah, because radius is going to be in meters. Period is going to be in. Hey, we're off to the races, right? So if we do a quick summary here, we got centripetal force equals mass times centripetal acceleration, which we said is mv squared over r, which is also m 4 pi squared r over t squared. Okay, it's the exact same thing. So if I tell you that Olivia is driving at 10 miles per hour, and we know the radius and we want to find the centripetal force, do this. If I tell you that Olivia is moving in a radius of 5 meters, and it takes 2 seconds for her to make 1 revolution, use this equation. Okay, so it just boils down to what you have in terms of an equation and what you're going to use. Now, one last thing and then we're done. So I'm going to take what's known as the green spinny thing. It's a highly technical term. And I'm going to put 2 quarters on the green spinny thing. One towards the outside and one towards the inside. Okay? So I'm going to make this thing go around like this. Now, are the quarters undergoing centripetal acceleration? Yes. Why?
Because they're moving in a circle.
They're moving in a
Circle.
The quarters want to move in a circle.
No.
No. Okay. They want to either remain at rest or move in a straight line. So, as this thing is moving, literally this, which quarter takes the longer amount of time to go around? The outside quarter, the inside quarter, or is it the same?
It's the same.
It's the same.
It's the same.
It's the same.
Which one? So look, okay, so we're here, right? So if you time that and it goes around,
Same time.
The one on the outside travels a greater distance.
no, that's not, I'm not talking about
It's the
distance.
same time.
Yeah, it's the same time though.
All I'm asking is time.
Same.
Are they both going to take the same amount of time?
Yes.
Yes. Now, which quarter is going faster?
Outside.
The outside one. Why?
Because it's traveling farther distance.
It has to travel a greater distance in
The same
same amount of time. So, with that being said, which quarter is going to undergo the greater is going to require the greater centripetal force to move in a circle? The outside quarter or the inside quarter?
Outside.
Outside quarter, because if you think about it, once it starts to move, T is going to be the same for both quarters. Mass is the same for both quarters. So what that means is that you could isolate this and just call it one constant, because the mass is the same, the 4 pi squared is the same, period is the same. So that means basically this is centripetal force is some constant times a radius. So as the radius gets bigger, what's going to happen to the centripetal force? It's going to get bigger. Now, here's my question. I want to make this thing spin faster and faster and faster. Which quarter will fly off first?
One on the outside.
The outside quarter, the inside quarter, or will they both fly off at the same time?
The outside.
There's more force applied to it, or more centripetal force acting on.
Okay, now here's the deal. What's creating the centripetal force?
Friction.
Friction, okay? Because remember, centripetal force in and of itself does not exist. Centripetal force only exists because of friction, tension, gravity, something like this. So, of the three, what's keeping these quarters moving in a circle? Friction. I don't have little strings tied to them. There isn't like a small black hole that I could put right here in the middle and it can keep them in order, which would be cool. So, there's going to be friction. Does friction have a limit on what it can do?
Yes.
Yes, okay, because if you exceed that limit, what happens? Goes flying off, right? So as I go faster and faster and faster, what's going to happen to the centripetal force needed to keep them in place? Greater and greater and greater, right? So if I speed up and go faster and faster and faster, outside one flew off first. Why?
It was moving more quickly.
Centrifugal force.
No. Do you think they both have the same amount of frictional force available to them?
Yes.
Yeah, okay, it's the same quarters, everything is the same. So you have a limit, right? So it would be like, here I've got this nice little rubber stopper on this thread and I swing it around, right? But the thread has a limit, okay? I can easily break this. So do you think I'm going to take this same thread and take Hank the bowling ball and try and swing Hank around on the end of the string?
Yes.
No, bad things are going to happen. Why? It's going to break. There's a limit to what the thread can do. Just like there's a limit to what friction can do on that quarter. So it's, the outside one exceeds that limit first because it's going fastest. Now, I can get the inside one to fly off, right? But I have to make it go a lot faster because it has a smaller radius, therefore it doesn't undergo as much centripetal acceleration. Now, what if I put that quarter dead middle?
It's not going to move.
It's not going to move. Why?
It's just spinning there.
Yeah, okay, because of the fact that if you look at this, it has no radius. If it has no radius, guess what?
There's no force.
There you go. Okay, stop that.
Wait, I need to see that in action.
Do you need to see this in action?
Okay.
Okay.
Bam.
So, read them actually. Now, here's the deal. When you get to question number 1, speaking of marching bands, okay? So, you've got two people, Betty Joe and Bobby Joe, and they're going to be marching. Here's the deal. They want to march, and they're going to be in line, okay? They're going to be going around like this. So, Betty Joe has a radius of 1 meter, right? Bobby Joe has a radius of 8 meters. It takes the line 30 seconds to go around and complete one revolution like this. All right? So that's the basis of this whole thing. Now, pay attention. How many significant digits did I give you in every one of those problems? 3. How many significant digits do you think I want in every answer? 3. Now, let me give you all a hint. If you write 0.004, for example, how many significant digits does that have?
1.
1. These are like freshmen. They're taking up space. They don't count, okay? You don't start to count until you hit an upperclassman, okay? Then you start to count. Zeros don't count. I want 3 significant digits in every one of those answers, okay? Don't make this difficult. On the back side, when you get to number, number 6, okay? So let me set the stage on number 6. So you're swinging the ball around on the end of a string like this, okay? Right? And you don't have a timer to measure how fast it's going. So what you're going to do is you're going to swing this thing around, and then you're going to let go of it. So as soon as you let go of it, what does it turn into?
A lemming problem.
Turns into a lemming problem. Okay? So number 6 is basically a lemming problem. You know it's going to be 1.8 meters above the ground. So knowing how high it is, you can figure out how long it takes for it to fall. Okay? Because it's going to be moving in a horizontal circle. You know how far it goes, so then you can find your Vx. Knowing your Vx, guess what? That's how fast it was going before you let go of it. Then you use that to figure out the centripetal force needed to hold that in. Okay? All right. You're on your own.